So we talked about removable discontinuity, which we defined to be a hole. And so this is where both of these conditions need to hold true. That the function itself is not defined, meaning there's an open circle, or it's not continuous, meaning the point does exist, but it exists in somewhat different than the line your pencil's on. And so the function could be defined for that value, or it could be redefined. So like if you think about with a limit, sometimes once we factor a limit, we're actually removing the hole. So let's go ahead and look at example 2 below. I've got this graph, and when x equals 2, you can see that the graph is continuous except at that point, and in our case the point does exist. Or if we were taking this function and factoring and canceling with the denominator, then this would go away and we would have a straight line. So that hasn't happened yet, so we still have hole discontinuity, but it's possible. The second is jump discontinuity, and so we said basically this is where the limit from the left does not equal the limit from the right, and so basically visually the graphs don't meet up, but it's not non-infinite. So sorry to make you dizzy, let's look at x equals 4 below. So when we look down here at x equals 4, we can see this section where our graph does not meet up at both places. It does happen to exist there is a f value at x equals 4, but these could have both been open circles and we would still have jump discontinuity. And the last type is infinite discontinuity, and this is where either the limit from the left or the limit from the right is infinity, or positive or negative. And we'll look at -3 down below. Now there's a slight mistake on this visual, but down here where x equals -3, only the limit from the left is negative infinity. This should have been an open circle, and the limit from the right would have been about -0.5. And so I just kind of restate all of that.